Hello everyone, how you all doing? Today we'll be talking about the epsilon delta definition of a limit. Most people didn't really understand this until their masters, it suddenly clicks for them. But I think it's very easy to understand, it's very intuitive, so I just want to explain how I see the epsilon delta definition, and how you can too. I think it's very nice to understand this. So what it is, let me use the blue pen for this, I'm sorry. For all epsilon greater than 0, so this upside down A means for every or for all. For all epsilon greater than 0, there exists, just E means there has, for all of these ones, there has to be a delta greater than 0, st, which means such that or so that, for the limit x to a of f of x equals L, 0 is less than x minus a, which is less than delta, and f of x plus L, sorry, let me write my L properly, plus L is less than epsilon. Okay, so you've probably seen this in your calculus class, and you're still like, oh, not this again, I don't want to learn this again, or, oh, I hate this, I don't even understand this at all. So what I'm going to do, I'm going to draw a graph for you, and let's hope we can understand this. So this is my x direction, this is my y direction. Alright, let me draw my function f of x. Whoa. And here is going to be a limit point. So you should know that a limit is something the function can never reach, but it can get very, very, very close to. And this is f of x. So of course it continues. It continues this way, continues that way, but I'm not going to draw that. Now let's say at this point here, this equals 7. And this is also going to equal a. So the limit, as you can see here, is like as the x-axis approaches the 7, and L is going to be here, the y-coordinate, which, let me just write this with black as well. This is going to be L, and, sorry, I keep writing my L's like this, I'm so sorry. L, and if you get closer and closer to 7 from the x-axis, you're going to get closer and closer to L. So we're going to understand this with epsilon and delta. So basically, I really already told you everything that you need to know. Alright. So let me just fill this in. So then what we can introduce a bounded region, a bounded domain, where this is 7 plus delta, and this is 7 minus delta. So the delta is really just arbitrarily small, or it can be as big as well. An arbitrary constant that you can add to a, and when you have that, let's say from here, you would take it, and and L would have a range from here to here. So here, like so. So this is what it is. So, and this would be L minus epsilon and L plus epsilon. So for any delta, you will see that as it approaches the function, you will have an L minus epsilon and an L plus epsilon. So the smaller this is, the smaller the difference in L is. And this is quite intuitive, right? So it's like the lesser the difference, the closer it will be to that specific limit point, which is as close as it will be to L. And if you're further and further away, the distance will be larger. Not necessarily, but most of the time, and for intuitive sake, it would be larger, wouldn't it? And this makes a lot of sense. This is just simply what the epsilon delta definition is all about. It's the notion of closeness. Alright. Now let me do one more thing to help you understand the epsilon definition further. Alright. So let us say we have x, so the absolute value of x minus 3 is less than 0.01. And let's just quickly solve this inequality, because we see lots of these inequalities in our epsilon delta definition, and let's see if this can help us. So, x minus 3 is less than 0.01. That means if you know about absolute values, this would be negative 0.01 is less than x minus 3, which is less than 0.01. Alright, now let's add 3 on both sides. I'll use a blue pen to show you. So we add 3 on each of them. So then we're making x the subject of it. So then x is greater than 2.99 and less than 3.01. Okay, so this makes sense, right? X is bounded between 2.99 and 3.01. That's the distance. So this is the distance, or let's say here, if x minus 3 was less than 0.101, that means the delta would be 0.01, and that's where it's bounded to. So if you have an epsilon delta question asking you, well, if delta was less than 0.01, what are the possible places? So we can remove delta, and we can have 0.01 minus 0.01. And this would be quite close that it'll be quite close to the function as well, quite close to L. But if we made the 0.01 smaller and smaller, maybe to like 0.00001, then that would be much closer and much closer to, that was way too many muches, much closer to this 7 or A, or in our above question it was 3, and that would make it much closer to L. So if the larger the delta, the more the wiggle room, and it will correspond to one and one only epsilon as well. So I hope this is an intuitive way of understanding epsilon delta proofs. A few other videos will be posted and added to what's it called, a playlist, where we will talk about more about epsilon delta definitions. So this is just the first lecture, maybe out of 3. I'll teach you how to do some epsilon delta proofs. Alright, so thank you very much. I hope you understood, and have a nice day. Do more maths. Thank you.